We're going to begin working through these algebraic problems here on homework number 6. So first we have a situation where there's a box with a mass of m sitting on top of a box with a mass of 3m. So there's my box with 3m, there's my box with m. And we want to know two things. How much force does a larger box exert up on the smaller force? And how much force does the floor exert up on the larger box? So what I'm going to do first is I'm going to draw a free body diagram for each object. So I'm going to start with object M, and the forces it has acting on it are this force going up, and that is from the larger box. So I'm going to call the smaller box A, larger box B. So I'm going to say that's the force of B on A. And of course we have the force of gravity acting down on the smaller box. And then when we do our forces on the larger box, we have the force of gravity, of course. We have the force from the floor, which I'm going to call the normal force. And we have the force from the smaller box, box A, pushing down on it. So the force of A on B. So for the first question, we're worried about solving for this force, the force that the larger box, which we're calling box B, exerts up on the smaller box. So I'm going to set up my F equals ma. This is for box M, the smaller box. So the forces that I have acting on it, I'm going to have the force of B on A minus the force of gravity. And that's going to be equal to mass times the acceleration, but the acceleration of this box is 0. It's just sitting there. So we can say the force of B on A is simply equal to the force of gravity acting on that box. We want to answer, though, in terms of m and fundamental constants. So I'm going to make that substitution that I know the force of gravity is equal to mg. Okay, and so that's going to be my answer to the first one. The force that the larger box exerts up on the smaller box is simply mg. So that solves part A. For part B, I'm going to do my F equals ma on the 3m box. So same setup here. We have the normal force, which is the force from the floor, minus the force of A on B, minus the force of gravity acting on that 3m box. That's going to be equal to 0 as well, because that box is not accelerating either. So two substitutions I can make here. First of all, I know that this force here, the force of A on B, is the same as the force of B on A, and that goes back to Newton's third law. Those forces that the boxes exert on each other are equal and opposite. So the opposite is the fact that they're in opposite directions, but the magnitude of those forces are equal. So I can say F of A on B is simply equal to mg, all right, which I found in part A here. And then minus the force of gravity, it's the force of gravity here acting on the 3m box. So that's going to be 3mg, making that substitution once again. And the reason I'm doing that is I ultimately want to answer in terms of m and fundamental constants. So I need to get that fg out of there. So I go ahead and solve for fn, moving both of those over to the right side and combining them since they have that like term there of mg. And I get that my normal force, which is the force from the floor, is equal to 4mg. Moving on to the next question, we have a baseball player running at a speed of v. The player slides into second base, coming to a stop, and the coefficient of kinetic friction between the baseball player and the ground is mu. And so we first want to find the acceleration of the baseball player. So, as always, I'm going to start with my free body diagram. For the baseball player while he's sliding, so we have the force of gravity going down, we have the normal force going up from the ground, and I'm going to say that he's traveling to the right, so that's going to be the direction of my velocity. So that means that my force of friction is going to be going back to the left. Now, you might be tempted to say that there's some forward force here. It's a pretty common thing. But if you think about it, there is no object that's pushing forward on the baseball player, okay? The force of the slide, the force of moving, those aren't objects, so there can't be a force from them. We can't say the baseball player is pushing forward on himself because he can't exert a force on himself. The reason why the baseball player is traveling to the right is not because there's a force going to the right. It's because the baseball player was already traveling to the right when he began his slide. Now, at some point, there must have been a force going to the right, but not right now. When he's sliding to a stop while traveling to the right, there is no force pushing him to the right, only this force of friction pushing him to the left and causing his acceleration to be going to the left, meaning he's slowing down because it's opposite the direction of the velocity. Now, we're going to go ahead and set up our max and our may here. We have forces in two directions. And you might be saying, but we don't know the mass, we don't know a lot of things, and that's okay. We're still going to set up max and may like we always do. So in the y direction, we have Fn minus Fg, and that's actually going to be equal to 0 here because my y acceleration is 0. And so I can say that my normal force is equal to Fg, which is really just mg. So I'm substituting in for the force of gravity. I know that my force of gravity is always equal to mg. Okay, so I know that the normal force is equal to mg. On the x side of things, I'm going to say negative ff because it's going to the left, and I'm going to use my standard sign convention, is equal to m times my x acceleration. I know that my force of friction is always mu k times my normal force when I'm dealing with static friction, and that's going to be equal to max. And I'm going to substitute in here. I'm told that my coefficient of friction is just mu. I solved for the normal force over here, so I'm going to sub in mg for my normal force, and that equals m times my x acceleration. That's what we're almost always doing for these friction problems, and I realize that you might not have seen this initially, but what ultimately happens is the mass cancels out, and it doesn't matter that we don't have it, and we end up solving for our x acceleration, which is simply negative mu g. If you had set it up differently, you might have gotten a positive answer, and I think the answer listed is actually just mu g, but that's okay. Either one would be acceptable. It all depends on what direction you pick to be the negative direction. Moving on to part B, we're told the baseball player slides to a stop over a distance of d, and we want to know how far would the baseball player slide if, and then we're given a few new situations. So what I'm going to do, this is one where we're going to set up our original and our new situation here to determine the new distance in terms of d, the original distance. So I'm going to start with my original situation and set up my kinematics for that. So we know that the distance is d, my initial velocity is this v here, all right, which we're told in the very beginning of the problem. I know my final velocity is 0, and I know my acceleration is negative mu g, and that's what I got in part A of the problem. Don't know anything about my time, don't care about my time. So I can say vf squared equals vi squared plus 2a delta x. So 0 equals v squared plus 2 times negative mu g times d. And when I go ahead and rearrange that, I get 0 equals v squared minus 2 mu g d. So v squared is equal to 2 mu g d. I can now go ahead and start looking at the impact that each one of those changes is going to have. So I'll start with that first one where we have 3 times as much initial velocity. So I go ahead and set up my kinematics chart once again. My new distance here I'm calling d prime just to distinguish the fact that it's different from that original, or at least it could be. We can't assume that they're the same. My new initial velocity is 3v because it's 3 times as much. Final still 0, and acceleration still mu g. So I'm going to use the same kinematics equation, that vf squared equation that I used before. So I'm going to plug in the things I know. 0 is my final velocity. 3v is going to be my initial. That entire quantity is squared. Plus 2 times negative mu g times d prime. I can go ahead and simplify some, and I get 0 equals 9v squared minus 2 mu g d prime. And so when I solve for 9v squared, I find that 9v squared is just equal to 2 mu g d prime. What I can do now, and I think the easiest way of combining these two equations, is I know that this is equal to v squared, and I can just substitute that into my other equation. So I can say 9 times 2 mu g d equals 2 mu g d prime. I find that a lot of things divide out here. The 2, the mu, and the g all divide out. And I'm left with 9d equals d prime. And so there's my answer to part 1. Part 2 asks what would happen if my mass was 3/4 as much. So I go ahead and set up my kinematics once again. My displacement is going to be d prime. Once again, I can't assume it's the same. My initial velocity will be back to v because we're no longer changing that. My final will still be 0. My acceleration will still be negative mu g. And you might notice that this setup is identical to this setup. So you can obviously go through and do this. But the easiest thing to say is just that d prime is equal to d. That mass has no change, and that really goes back to the fact that in part A, we divided out the mass. The mass really didn't have an impact. For the last one, we're asked what would happen if it's raining and the coefficient of friction was half as much as it was. So we're going to go ahead and set up our kinematics one last time. Our displacement is d prime, initial velocity is v, final is still 0. The one thing that's going to change here is our acceleration is going to now be negative 1/2 mu g, because that coefficient of friction did change, and our acceleration depends on that. So I'm going to set up my kinematics once again using that vf squared equation. So plugging in what I know, I have 0 equals v squared plus 2 times negative 1/2 mu g times d prime. So I get 0 equals v squared minus, and the 2 and the 1/2 cancel out. So minus just mu g d prime. So that means that v squared equals mu g d prime. I can now take this equation here and compare it to this equation here. And I'm just going to set them equal to each other because they're both equal to v squared. So I can say 2 mu gd equals mu gd prime. The mu and the g will cancel out here, divide out, and I find that 2d is equal to d prime, and that's my final answer. Moving on to number 3 here, we have a box sitting on an elevator that is accelerating upwards at a rate of a. While it's accelerating upwards, a person pushes on the box horizontally, and we have some friction between the box and the ground, and we want to know an expression for the maximum horizontal force that a person can exert while still keeping the box at rest. So we start, of course, with our free body diagram. We have our normal force going up. We have our force of gravity going down. We're pushing it to the left, or at least that's the way it appears in the diagram. So that's the way I'm going to draw it. And my force of friction then is going to be going back to the right. In this situation, we know that we're accelerating upwards, so I'm going to draw that force off to the side. So I'm going to set up my max and may as I always would. In the y direction, we have Fn minus Fg, and that's going to be equal to m times that upward acceleration a, which we're told in the problem. It's accelerating upward at a rate of a. This is a little bit different than some of the ones we've done before. Normally we don't have a vertical acceleration, but in this case we do, and we can handle it using our F equals ma. I'm going to substitute in for the force of gravity like we normally do, so Fn minus mg equals ma, and we always solve for Fn when we're doing these friction problems, so I'm going to solve for Fn. It's going to be equal to ma plus mg. You could simplify it and factor out the m's, or you could just leave it the way it is. In the x direction, I'm going to set up my F equals ma as well, so I'm going to have my push, and I'll say that's negative because it's going to the left, plus the force of friction. And that is going to be equal to 0 because it does say what is the maximum force we can exert while still keeping the box at rest. So really what that should say is keeping the box from sliding. So I can go ahead and do a little rearranging and say that Fp is equal to my force of friction then in this case. And I can substitute in for friction mu s times Fn. One quick note, we have talked in class about how with static friction, it's always less than or equal to the normal force. Because we're worried about finding the maximum horizontal force, that's an indication that this less than or equals to is just an equals to sign in this situation. So I can make that substitution there. So plugging in the expression I just found for my normal force, I find that Fp is equal to mu s times ma plus mg. And there I have an expression for my pushing force in terms of A, mu, m, and fundamental constants. If I did want to factor out that m, I would end up getting Fp is equal to m times mu s times the quantity A plus g. Either one would be an acceptable answer. It's just a matter of how you simplify it. Moving on to the next one, we have a big sofa here with a weight of W. Remember, weight is equivalent to the force of gravity. We're told the coefficient of static friction between the ground and the sofa is mu s, and the coefficient of kinetic is mu k. So movers exert a horizontal force of the magnitude of F on the sofa. And we have two situations. We want to know the force of friction if F is enough to make it move, and if F is not enough. All right, so starting with A, I'm going to set up my free body diagram here. We have Fn, Fg, we'll say we're pushing it to the right, and we have a force of friction going back to the left here. Setting up my max and may, as I always do. In the y direction, I'm going to start with that. I like to start with that with friction because we know we need to find the normal force usually. So I'll say that Fn minus Fg is equal to 0 because in this case we are not accelerating horizontally. And my normal force then is equal to the force of gravity, which in this case we don't know the mass of the sofa, but we do know the weight, and weight is the force of gravity. So I can just say that Fn is equal to the weight. Okay, keeping in mind that weight is synonymous with the force of gravity. So now I want to know what is the force of friction acting on the sofa. I don't actually have to set up my max, although I could in the x direction. It would simply be Fp minus Ff equals max. But the key is solving for this force of friction. So I know that this is a case where the sofa is moving, where the sofa is sliding. So my force of friction is going to be kinetic, which is simply mu k times my normal force. So it's going to be mu k, which I'm given as one of my constants, times w, which is equal to my normal force that I solve for in my y equation. So there's part A, and this really illustrates the easy part about kinetic friction. You know what kinetic friction is equal to. All right, you don't have to worry about whether or not it's less than or equal to. Kinetic friction is just equal to mu times the normal force. Moving on to part B, we're now asked about what happens if the force is not enough to make it move. So our free body diagram is really the same as part A. None of those forces have changed, or at least the forces that exist acting on the object have not changed. And in the y direction, everything is the same. So we actually can still say that the normal force is equal to our weight. What does change, though, is the x direction and something about our friction. So now we're dealing with that situation where friction is less than or equal to mu s times our normal force. So we can't use this to solve for our force of friction because we don't know for sure if friction's at a maximum here. We can solve for what the maximum force of friction would be, but that doesn't necessarily make it the force of friction in this situation. So what we have to do here is we have to go ahead and set up our forces in the x direction. So sum of the forces in the x is equal to max. So we're going to have Fp, that pushing force, minus the force of friction, and that's going to be equal to 0. That we do know. If this force is not enough to make the sofa move, the acceleration of the sofa is 0. So our pushing force, we're told, is just F, and we move that force of friction over, and that's what the force of friction is going to be equal to. Okay, it's just going to be equal to whatever that pushing force is. In this case, that's F. And this actually illustrates the tricky part about static friction. Because of that less than or equals to sign, a lot of times we have to just solve for the force of static friction using our F equals ma rather than mu times our normal force, like we did with kinetic. Okay, moving on to our next problem, we have a coffee cup sitting on top of a car as a girl drives to school. And we're given the coefficient of friction between the cup and the car, both static and kinetic. Okay, so I know the first one just asked what force causes the cup to accelerate forward, but I'm going to start out by drawing my free body diagram for the cup. We have our normal force going up, of course, force of gravity going down. It's accelerating forward this way. So, what force is actually keeping it moving forward? Well, let's think about what actually is touching it, what objects we possibly have. The only object we really have is the car. And so as weird as this sounds, the force that's making it move forward is the force of friction. And this is what I would think about. If there wasn't any friction, what would the cup do? If there was no friction, the car would accelerate forward, and the cup, due to the lack of unbalanced force acting on it, would just stay in place. So we said that friction, at least static friction, acts in the direction opposite the direction that the object wants to move. In this case, it's really not the direction the object wants to move, it's that the object doesn't want to move at all, and friction is the force that makes it accelerate forward. So that answers question A here. What force causes the cup to accelerate forward? It is the force of friction acting on the cup. Moving on to part B, we want to know what is the maximum possible acceleration that we can have before the cup begins to slide. So for that, we're going to set up our max and may. In the y direction, we have the normal force minus the force of gravity. That's equal to 0 because we have no vertical acceleration. So like many other problems before, our normal force equals mg. I never get in the habit, though, of assuming it's equal to mg unless I can show it with my F equals ma. For the x direction, sum of the forces in the x equals max. We have just the force of friction here. It's going to be equal to m times ax. For that force of friction, we know it's before it begins to slide, so I'm dealing with static friction, which has that force of static friction is less than or equal to mu times my normal force. Because I'm worried about the maximum acceleration, I can say that that force of static friction is not less than or equal to, but simply equal to. So I can make the substitution now that mu s times fn is equal to m times ax. I know my fn is just mg, so mu s times mg equals max. The m's divide out here, and what I'm left with is that mu s times g is equal to my maximum acceleration in the x direction. Moving on to part C, I want to know if I have these given coefficients of friction and mass. I want to know if the car accelerates forward at a rate of 7 meters per second squared, will the cup slide off of the car? And what is the force of friction acting on the cup in this situation? So what I'm going to do is I'm going to use this expression that I just derived. The maximum possible acceleration before it slides is simply equal to mu s times g. And so I can find that my maximum possible acceleration is 0.8 times 9.8. Okay, and I get that my acceleration here, my maximum, is 7.84 meters per second squared. So to answer part 1, will the cup slide off the car? The answer is no. The maximum acceleration is that coefficient of friction times g, as shown in part B. So we can have an acceleration of up to 7.84 meters per second squared before it begins to slide. For part 2, what is the force of friction acting on it in this situation? Two important things here. Number one, we know that it's a situation where it's not going to slide, so we are dealing with static friction. And number two, we've also now proven that we're not at our maximum force of static friction. we can't now say that the force of friction is equal to mu times our normal force. However, what we always can do is think about our forces in the x direction, and that's what we're going to do here. So for part 2, I'm just going to think about my forces in the x direction, because I can't assume that my force of friction is equal to mu times my normal force. So I'm going to say my force of friction is equal to ma, the mass of the cup, 0.5, times the acceleration of the cup, which I know is 7 in this situation, because that's how quickly the car is accelerating forward, and therefore the cup is accelerating forward at the same rate. So I can say that my force of friction is simply 3.5 newtons. Moving on to the next problem, we have a Jamaican bobsled going down a hill that's slanted at an angle of theta. Coefficient of friction between the blades and the sled is mu k, and we want to calculate the acceleration of the bobsled in terms of theta, mu k, and fundamental constants. So first thing I'm going to do, as always, is draw my free body diagram. We're now dealing with an incline. So I'm going to draw my forces on an incline. We have the force of gravity going straight down. We have a normal force going perpendicular to the incline. And we have our force of friction sloped at an angle of theta there. So there's my theta. And the first thing I'm going to do is, since I'm tilting my axis for it being on an incline, I'm going to break the force of gravity into its x and y components. Whatever the angle of the incline is, that's that upper angle there. So that means that this x component is fg sine of theta. This y component is fg cosine of theta. And keep in mind, as I'm setting up my max and may, I've replaced fg with its x and y components, so we won't see fg by itself anywhere in these equations. Next thing I'm going to do is set up my f equals ma in the x and y direction. So in the y direction, I have Fn minus this y component of gravity, so Fg cosine theta, and that's equal to 0 because perpendicular to the incline in the y direction, in our new y direction with our tilted axis, the object's not accelerating. So I can say that Fn equals Fg cosine of theta. So Fn is simply mg cosine of theta. In the x direction, some of the forces in the x, we have the x component now of our force of gravity, which is Fg sine of theta, minus our force of friction, and that's going to be equal to m times our x acceleration. We are going to be accelerating down the incline in this case. I'm going to make two substitutions here. I'm going to say that Fg is just mg. Okay, we don't know the force of gravity, but I do want to get that g in there, so I'm going to make that substitution. So mg sine theta minus mu k Fn, because that's what my force of friction is equal to max. So I have mg sine of theta minus mu k times this normal force that I solved here in my y direction, mg cosine theta, and that's going to be equal to m times ax. I have a mass in every single term, so now I can cancel it out. You do want to be a little careful. We can't quite cancel mass out in this step because we don't have one in every single term. Okay, so this is one term, that's one term, that's one term. In order to get rid of mass, you have to have it in every single term because you're dividing it out of both sides of the equation. And so what we're left with is an expression for our acceleration, g sine theta minus mu k times g cosine theta. And if you want to be fancy here, you can factor out that g and say g times sine theta minus mu k cosine theta, and that's your acceleration. But you certainly don't have to do that. That first one is a perfectly acceptable answer. All right, up next we have the static coefficient of friction between an icy road and the tires of a car is mu s. What is the steepest possible angle that the car can park on a hill without sliding. I'm going to set up my free body diagram here once again. So we have our car on an incline, we have the force of gravity going down, normal force going up, and in this case it's static friction, but it's going up the incline because the car, if there wasn't static friction, would slide down it. So that static friction is going to oppose the direction the car wants to slide. As always with these incline problems, we're going to tilt our axis and then do the components of the force of gravity. I'm going to call the angle of the hill theta. It doesn't define theta for me, but that actually is ultimately what I'm looking for. And whatever that angle of the hill is here, that's going to be that upper angle in my triangle for my components of gravity. So I have in the x direction, Fg sine of theta, and in the y direction, Fg cosine of theta. Setting up my forces in the y direction, like I always do, we have normal force minus Fg cosine theta equals 0, because we're not accelerating in the y. So my normal force equals mg cosine of theta, because I'm substituting in for Fg. Fg just equals mg. So there's my y. Over on my x side, we have Fg sine of theta minus Ff, and we want to know the steepest angle that the car can park without sliding. So that means that my acceleration in the x direction is also 0, right? In the y it was 0 because we're not accelerating relative to the incline. In the x it's 0 because the object's not moving, not sliding at all. Two things I can do here. Number one, I can say Fg is simply mg, so mg sine of theta, and I can substitute in for my force of friction mu s times my normal force. Once again, I always want to justify why I can make that substitution, because my equation for force of friction is simply Ff is less than or equal to my normal force. Because it's asking for the steepest possible angle before the car starts to slide, that is an indication that the force of friction in this case is equal to the maximum, so I can make that substitution. And so I can say mg sine of theta is equal to mu s times my normal force, which I found over in my y, so is equal to mu s times mg cosine of theta. Both the m's and the g's divide out, and what I end up getting is that sine of theta is equal to mu s times cosine of theta. Here's the slightly tricky part, and this is something that either is going to be a new piece of information or a review from pre-calc. There's a nice little trig identity that we have, which is that sine of theta divided by cosine of theta is equal to tangent of theta. And that's really important in this situation. And here's why that's important. I have a theta on this side and a theta on that side, and I want to ultimately solve for theta. So I can't just divide by sine or divide by cosine to get theta by itself. It doesn't quite work that way. So whenever I have a situation like this, and I have both a sine of theta and a cosine of theta, I'm thinking about this identity right here and thinking about how I want to ultimately be dividing sine of theta by cosine of theta to get tangent of theta. So that's exactly what I'm going to do. I'm going to divide both sides by cosine of theta. And what that's going to do, on the right side, it's going to divide out that cosine of theta. And on the left side, it's going to turn that sine of theta over cosine of theta into a tangent of theta term. And now I can solve for theta by taking the inverse tangent of both sides. And so I get that theta, when I take the inverse tangent of that left side, that's all that's left, is equal to the inverse tangent of that coefficient of friction. And there is my final answer. For our next problem, we have a block with a mass of m hanging on a vertical spring with a spring constant of k. They're taken to an elevator that accelerates from rest to a speed of v over some period of time t while traveling up. And we want to know how much the spring is stretched before the elevator starts moving, while it's accelerating, and after it's reached a constant speed and continues upwards at that constant speed. So in all these cases, I'm going to start with my free body diagram. We have the force of gravity going down on this block, and we have the spring force going up. And so we're going to have some of the forces in the y equals may. My equation is always going to be Fs minus Fg equals m times ay, and I can actually substitute in for Fs. I know that it's always equal to kx. That's Hooke's law there. And Fg is always equal to mg. So that's always going to be equal to may. So this equation is going to be true always. What might change, though, is our acceleration, and therefore what's also going to change is how much that spring is stretched or compressed. So let's start with A. How much is the spring stretched before the elevator starts moving? Well, I can say kx minus mg equals 0, because in this case, my y acceleration is just going to be 0 since the elevator is not yet moving. So I can go ahead and solve for x. I can say kx equals mg. So the amount the spring is stretched or compressed is simply mg divided by k. Moving on to part B, same basic equation, but now I actually do have an acceleration. So kx minus mg is equal to m times my y acceleration. I'm going to go ahead and solve for my y acceleration using some kinematics. So we know we start from rest and we accelerate to a speed of v over a period of time t. So I can solve for that acceleration. I'm just going to use my definition of acceleration, vf minus vi over t. So it's going to be v minus 0 over t, or just v over t. So that's the value of my acceleration while I'm speeding up. So I can plug that in over here, and so then I'm left with kx minus mg equals m times v over t. I can go ahead and move that mg over, and I get kx equals m times v over t plus mg, and that means that x is equal to m times v over t plus mg all over k. All right. You could simplify that slightly differently. You could factor out that m, but what I have right there is an acceptable answer as well. For the last part, for part C, how much is the spring stretched after the elevator reaches a constant speed of v, and its speed remains constant? We're again in a situation where acceleration equals 0, so it's actually identical to part A. Whether or not we're moving or not moving, if our acceleration is 0, our forces are balanced. So we can say that kx equals mg once again. So my x in that case is just going to be mg divided by k. No different, right? Traveling at a constant speed in terms of forces is no different than being at rest, because both are situations where we're not accelerating.